Hello everyone and welcome back to our Python Climate Health Data Science workshop. I'm Chi and today we will be talking about another very important tool in Python for climate data analysis. So in our previous sessions, we worked with geospatial raster data using Rasterio and GeoPandas to analyze climate patterns across Ghana's region. While this approach worked well for basic analysis, climate data often present us with more complex challenges. As climate data typically contains multiple dimensions, for example, time, latitude, and longitude, which are all interacting together. And this is where Xarray comes in. It is a powerful library specifically designed for this multidimensional data structure. So what makes Xarray particularly useful? Well, it introduces labeled dimensions, coordinates, and attributes on top of regular NumPy arrays. And these labeling systems make our data more intuitive to work with and enables more sophisticated analysis. And with Xarray, we can perform, for example, when working with climate time series, Xarray makes it very straightforward to perform temporal queries and resampling operations, which is essential task for analyzing trends over time. Besides, Xarray is also good at handling multi-dimensional operations, as it supports broadcasting and vectorized operations on multi-dimensional data, which will make complex climate modeling and data aggregation more straightforward. So first, let's take a look at how Xarray actually organizes data. And at its core, Xarray builds upon NumPy arrays, but adds crucial features that makes working with complex climate data much more intuitive. So, as we know, traditional NumPy arrays are powerful but can be limiting when working with climate data. For instance, if you have temperature reading across different times and locations, it became difficult to keep track of which array index corresponds to what time or location. And this is where Xarray label dimensions become very useful. So Xarray introduced two main data structure, that is data array and datasets. And let's break this down. So a data array consists of four key components. First is value, and this is where your actual data, a regular NumPy array holding all your measurements. And second is dimensions, and these are names for each axis of your array. So in climate data, you'll typically see dimensions like time, latitude, and longitude. And instead of remembering that axis 0 is time, you can directly reference the time dimension, which makes the data more readable. And third is the coordinates. And coordinates label each point along your dimensions. For example, actual dates along the time dimension or specific latitude and longitude values for spatial dimension. And this makes selecting data much more natural. And you can just say, for example, give me data from January 2020 rather than give me index 24, for example. And finally, we have the attributes. An attribute holds the metadata about and you can think like units of the measurement, what kind of scale factors you have, what's the data source, and this metadata travels with your data and making your analysis more reproducible and clear for users to understand. And if we look at this diagram, you can see how these components come together. So each colored block represents a data array. So the blue one in this case might be temperature data, and the pink one here is the precipitation data. And you'll notice that how they share the same, for example, the coordinate system as shown by the orange, which red refers to longitude and latitude, and orange refers to latitude. And also the dimensions, as I just said, you have typically the time and also the X and Y. And so what is a data set? So actually a data set takes this organization one step further, and you can think data sets as a container that can hold multiple related data arrays. And in our diagram, you can see how temperature and precipitation data can be stored together, which share the same coordinate system. And this is quite similar to a pandas data frame, but capable of handling multiple dimensions more efficiently and more clearly. And the practical benefits of this structure will become more clear when you're working with real climate data in later of this tutorial. For example, if you want to analyze heat patterns in Ghana over the past years, you can simply select the data using meaningful labels like time and location coordinates rather than dealing with, as we said, the array indices. And this will make your code both easier to write and easier to understand. Now, let's see how we can apply Xarray in action. First, we're going to create a toy dataset, and this will help us understand how this data structure works in practice. And to begin with, we'll import the necessary libraries. So we're going to use several key packages. So Xarray for our main data structure, again, NumPy, Pandas, and also a few other packages. But specifically, we're also going to use what we call real Xarray package to load GeoTIFF files directly into this type of Xarray structure. And this will allow us to maintain all the spatial information while gaining the benefits of Xarray's label dimension and coordinates. So first, let's start by creating two sample arrays, temperature and precipitation. And we'll make these 100 by 100 grid cells representing latitude and longitude. And also we'll have the data for 30 days, so a month. And for temperature, we're generating random values between 20 and 100, which are in Fahrenheit. And while precipitation values, it will range from 0 to 10. And this simulates a very simple climate dataset. So we're going to use the NumPy random integer function to create this precipitation data. So as again, we can see that it's 100 by 100 by 30 grid size. And then the precipitation. And again, now for our time dimension, we're going to create a sequence of 30 daily timestamps starting from January 1st, as you can see here. And for this, we're using the Pandas date range function, which gives us nicely formatted datetime objects. And we can also check the length of our time object. And we can see that it has 30 elements, which correspond to 30 days. And then we're going to create our coordinate value. So the line x equal to list range from 1 to 101 creates a list of number from 1 to 100, which will serve as our x-axis coordinates. And we will do the same for our y-coordinates. And this value will give each point in our grid a unique identifier. And let's look at how we can create first the temperature data array. So when creating an Xarray dataset, we need to specify 4 key components, as we said before. So first is the data parameter, and this is our raw numerical data. In this case, it will be the temp variable that we just created. And these are our NumPy arrays containing the actual temperature values. And then for the dimension parameters, this is a list specifying the name of our dimensions. So we have x, y, and also our time dimension. And again, you can think of these as the axis of our data cube. The order matters here and should match the shape of our input data. So as you see before, the shape is, as we see before, we have the width, height, and also the depth. And that's x, y, time. And third is the coordinate parameter, and this is where we map our dimension names to actual coordinate values. So we're going to create a dictionary where x will map to our x coordinate list, y will map to our y coordinate list, and time will map to our time values from the Pandas data range that we created. And finally, we have a name parameters, and this will give our data array an identifier. And in this case, temp will be temperature, and the name will become very important when we combine multiple data arrays. So if we run this code, we're going to see that we indeed create the temperature Xarray data array. And here you can see the structure of our data array. And we can see that we have our coordinates, x, y, and time. Also, we have the index. And similarly, we do the same for our precipitation. And as again, you can see here, we have our data array for the precipitation, which share the same coordinates and dimensions as our temperature data set. So after we have created two data array, we can now combine them into a single Xarray dataset using the xr.merge function, and the resulting dataset will show both variables sharing the same coordinate system. And that is one of the key advantage of Xarray's model. So here we can see that we still have the same dimension and coordinates, but now we have two data variables, and that's how intuitive or convenient that by using Xarray, it can easily combine two data arrays into a data set with two data variables, in this case, temperature and precipitations. And this type of organization makes it much easier to work with multiple related variables compared to handling separate NumPy arrays. So this simple example demonstrates the power of Xarray's label dimensions and coordinates. In real climate analysis, this structure also becomes very useful when dealing with actual temperature and precipitation data across different locations and time periods. So now we have created our dataset, we can explore what makes Xarray dataset particularly useful for our data analysis. And one of the key advantages of Xarray dataset is their ability to efficiently organize multiple related data arrays. And accessing data in the Xarray dataset is straightforward. So if we want to work with, for example, the temperature data, we simply can just use ds.temp, and here it will directly access the data array of the temperature variables. And same for the precipitation data. And this labeled access is much cleaner than working with numerical indices, which is what we have to do if we are using a plain NumPy arrays. And another practical example is calculating the correlations between different variables. In this case, we can calculate the correlation between precipitation and temperature over time. And to do so, we can just simply use Xarray's built-in correlation function, the xr.correlation. And this single line will calculate the correlation along the time dimension for each spatial point in our grid. And as again, in a regular NumPy array, this kind of operation will require more complex indexing and explicit loops. So this is how intuitive and how powerful Xarray can be. Now let's move from our toy example to work with real climate data. And in this session, we'll be using real Xarray to handle our maximum heat index data for 2016. First, let's understand what real Xarray actually does. So real Xarray is an extension of Xarray specifically designed for geospatial data analysis. And the core function to use here is the real.openRasterio function, and it does several important things. First, it reads the geotip file and preserving all their geospatial metadata. And secondly, it will automatically handle coordinate reference system, the CRS. And third, it will mask the missing data values with NumPy num for cleaner analysis. And also, it offers efficient data chunking in this case through integrating with Dask, which we will introduce in the end of the tutorial. But for our analysis, we'll first need to locate our data files, and we're using the globe function to get a sorted list of all our geotip files for the year of 2016. And also, we're printing the first 5 files to make sure that they are in the right order along time. Now comes to the interesting part, loading all the 366 files into a single Xarray dataset. But there's an important caveat here. So while we are loading all files directly into memory for this tutorial, this isn't always the best approach for real-world application, because often when we are trying to access or read large climate datasets, you could quickly run into memory limitations. But in this case, since the heat index is a relatively small dataset, our computer still have enough memory to process this. So now let's break down our loading process. So first, we're creating an empty list to store our data arrays, and then we're having a for loop. So for each file in our file directory, we're gonna first open it with real Xarray, and we're gonna set the masked parameter equal to true to mask all the non-values. And then we're going to select the first band. In this case, we only have one band. And we're going to name each data array HI max, which represents heat index maximum. And finally, we're going to append it to our list. So we can run this code, and since we have a year of raster file to deal with, it will probably take a bit of time. And now we can use the xr.concat function to combine all the data arrays into a single data set along the band dimensions. And again, here we are loading all the raster files into our memory. And now you can print this data array, and as you can see, we have a band dimension which corresponds to actually the time. So starting from January 1st to December 31, and the y and x. So y will be the height and x will be the width. And from the printed data array, you can also see some non-values in our data, and these are the masked values that might represent areas outside of our region of interest or missing data points. And this automatic masking helps to ensure our following analysis won't be skewed by invalid data. And if we look at our loaded data structure, you might notice something interesting. So while we have 336 bands representing each day of 2016, we don't really have an explicit time dimension. But we could make our data more meaningful by properly incorporating time information. So how to do this? First, we can create a time index using the pandas data range function and set the period of to a year. And if we print the time list, we can see that it's a date list starting from 2016, the 1st of January until the end of the year. And now what we need to do is to integrate this time information into our data sets. And we're going to do this in 2 steps. So first, we can rename the band dimension in our Xarray data array to time. This makes more sense since each band represents a different day. And then we're going to assign our newly created time values to this dimension. And now if we plot this, we can see that it has been modified. So the band dimension has been renamed to time. And if we open this, we can also see that now in the time coordinates, we have an array of datetime objects. And additionally, we can also improve the readability of our spatial dimensions. So instead of using a generic x and y coordinates, we can also rename them to longitude and latitude. And this makes the data more intuitive for anyone working with geographic information. And now, we can see that we have our time dimension, latitude dimension, and longitude dimension, which is much more easier to understand. And finally, let's talk about data sharing in climate science. So often exporting Xarray to NetCDF format is a very common practice in the field of climate or environmental science. NetCDF stands for Network Common Data Form. It is a set of software libraries and machine-independent data formats that support the creation, access, and sharing of array-oriented scientific data. It is particularly useful because it preserves all our dimensional information and maintains our data organization, while it also supports efficient data sharing as it's compatible with many scientific tools and libraries. And in Python, the way to export our Xarray object to CDF is using the function called toNetCDF. So it's quite straightforward. So first you specify the output file path. In this case, I can name it at hemax-ghana2016.nc, and then to use the toNetCDF to run this. And this will export the Xarray data array to a NetCDF datasets. So now let's look at how we can read back our NetCDF file using Xarray. And this is very straightforward. We can use the xr.openDataset function with our file path to load the dataset. And then we can set the spatial-ref as the coordinates. This can allow geospatial operations. For example, if you want to reproject to automatically access and use this information to ensure accurate spatial analysis. And after we load this, we can print the loaded Xarray datasets. And as you can see, we have the time and latitude and longitude dimensions, and we have the data variables of heat index maximum. And however, there is something interesting happening behind the scenes that worth understanding, because as you can see here, in this case, when you print the Xarray datasets, you don't see the actual value got printed. But previously, we can see the array value got printed. And this is what we call a lazy loading strategy for Xarray. So Xarray use the lazy loading when working with NetCDF files. And this is a very smart approach where the data isn't immediately loaded into memory. Instead, Xarray will just read the metadata and structure of the file and waiting until you specifically request the data before loading it. And you can think of it like looking at the menu before ordering your meal. You can see what's available without having everything prepared at once. And this kind of lazy loading approach is particularly useful when working with large Climae datasets. For example, you might have a terabyte scale of dataset, but only need to analyze a specific region or a small time period. And with lazy loading, you can examine the dataset structure and prepare your analysis operation without consuming large amounts of memory beforehand. And when you are ready to work with the actual data, you have two options. So if you want to load the data, you can use the ds.load function to explicitly load all the data into the memories, or you can just access specific variables. For example, here we can just access the HI max, and this will just load the specific variables that you specified. And now let's try to explore how we can subset our data in Xarray, which will help us to focus on specific regions or specific time periods. So Xarray provides two main methods for subsetting data. First is the select function, which will allow you to select by label, or the iSelect function, which is for selection by integer index. To make it easy to understand, you can think of select as picking data by meaningful names or values, while the iSelect function works more like traditional array indexing that we learned before with NumPy. And here we can look at some practical example. First, we can subset our data by the time range. For example, if we're interested in analyzing only the summer heat patterns, we can use the function, we can use the select function and then slice the time dimension only from the months of June to the end of August. And if we print this, you can see that this only gives us the summer months from June through August. If you check the time dimension, you can see that it starts from June 1st until August 31. And you can notice how intuitive this is. We can just specify the actual dates rather than trying to calculate the array index. And we can also subset spatially using the latitude and longitude dimensions. So for example, here in this code, we're trying to subsetting or clipping our datasets to a specific geographical region that is bounded by latitude from 7 to 10 and longitude from -1 to 1. And you'll notice that here the latitude values are in descending order, which is common in climate data because higher latitude value typically represents more northerly locations. And if you run this, you will also see that the range of our latitude and longitude has been shrinked to the value range that we just specified. And for more traditional array style selection, we can use the iSelect. This line of code will select the rows from the 61st through 90 and also the column of 31st through 70 of our data. And now let's see how convenient and intuitive it is to analyze heat index value across different timescale. So what's particularly nice about Xarray is how convenient it makes these temporal calculations. And again, instead of dealing with complex state manipulation or index arithmetic, we can use natural descriptive commands that make our analysis more readable. So for example, if we want to calculate the annual mean heat index across Ghana, and you can just use this one line of code using the mean function and then specify the dimension will be time. And as you can see, now we have a 2D array in this case, and this will give us a broad overview of the heat patterns across the entire year. By averaging over the time dimension, we'll get a single value for each geographic location that represents the annual mean maximum heat index for the year of 2016. And again, if you want to calculate the monthly average, then you can use the group by function, specifying time.months and then add the mean function in the end. And this will aggregate our data into the monthly level. And also you can see that now we have a new coordinate or new dimension called months, which is from January until December. And same for the seasonal, you can also aggregate our data to the seasonal level. And you will also get a season dimension, which is first winter, December, January, and February, spring, and then spring, summer, and fall. And now let's visualize our analysis result and save them for future use. So to create the visualization, we first need to extract the raw data from Xarray. And since we already have the annual mean heat index, and then we just use the dot data to access the data. And then we can use the image show function, as we learned before, to plot the map. Now we have the average daily maximum heat index for Ghana on 2016. And after we have the map, we can actually also save this daily average heat index as a GeoTIFF file for future use or sharing. So first, we will need to get the metadata from our original files to maintain the correct geospatial information. And then we can just use the rasterio open function and .meta to get the metadata. And then we can create our output file path. And then you can use this code and use the with rasterio open function to export this data to the data folder and name it at heatmax 2016 average. And if you run this, and if you go to the code again, you can see that we just export the heat index for Ghana. And we can also check the output file that we just created. So finally, let's talk about Dask, which is another important enhancement for working with large Climae datasets, and how to integrate the use of Dask to our Xarray operations. So when dealing with Climae data, we often face a significant challenge. That is the datasets that are too large than our computer's memory. Well, Dask provides a powerful solution to this problem. It is a flexible parallel computing library that helps manage large datasets by breaking them into manageable pieces. So the key concept here is chunking. You can think of this as dividing our large datasets into smaller blocks or chunks of data that can be processed independently by our computer's CPU. And when we integrate Dask with Xarray, we can handle large dataset more efficiently. And in this code example of loading a NetCDF files, we can see that here we add a new parameters, which is chunk, and this will tell the Dask package to automatically determine appropriate chunk size for our datasets. So again, if we're loading heatmax map for Ghana from 2016, we can now specify the chunk size as auto and also print our data of our Xarray datasets And for example, we can perform an operation and see how Dask will actually handle this. So here we're calculating the mean, again, the mean of our heat max across time. And then now if we print the structure of our main temp, here you will see a figure which shows the size of our data sets. We can see that we have two columns. One is named array and the second is named chunk. So array refers to the actual total array size of our loaded data array. And chunk will represent how Dask in the back of the processing will handle our data array, dividing them by chunks. But here we can see that we only have one chunks, and the chunk and array share the same size. And this is because our data sets is too small. It's not big enough. But for example, if the shape got to, for example, 10,000 by 10,000, then the chunk, and then Dask will determine a suitable size for the chunks, and then you'll have multiple chunks that consist the total array. And this chunked processing will become particularly useful when we are working with real-world climate data sets, which can often be hundreds of gigabytes or even terabytes in size, and allow us to perform complex analysis on large data set without requiring enormous amount of RAM. And here, if we just access the original DS Emacs variables, we can also see our data in a 3D dimension cube. And again, here we only have one chunk, and that is because our array is not big enough for Dask. And this is all for today. I hope you enjoyed today's session. And again, as we said before, there are tons of other available documentations and tutorials, and I would highly encourage you to check what more we can do with Xarray and Dask.